Hey everyone, welcome to the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops into your brain, just write it down, gather them up, and I'll answer them here. I just want to give a sort of a reminder that, people ask me like how they can support, how they can help out what we're doing with Universe Today. And Universe Today isn't just me. It's a giant team of writers. Most of our energy is spent writing articles over on the Universe Today website, but also recording the podcast versions of everything we do, as well as doing the YouTube videos and a lot of other projects. So the best way to participate in that is to join our Patreon. And if you've been enjoying our content for years, maybe decades, because we've been doing this for 20 years, and you're feeling a little guilty and you have some money to spare, then join the Patreon. Go to patreon.com/universe today, and you get an ad-free version of the website, which looks much nicer. You get sort of more behind the scenes stuff. Sometimes you get some ads in advance, but you also know that you're helping to create the content that we are working on. And it allows us to be completely independent, not beholden to any grants or investors or anything. We're just doing this for you. And you can even just sign up for Patreon for 1 month, cancel right away, and you'll still get the ad-free version for the rest of your life. That's how little ad revenue we make. That, if you donate $3 through Patreon for 1 month, no ads for the rest of your life. So if you're feeling guilty, if you're feeling like you really need to support what we're doing, go to patreon.com/universe today. All right, let's get into the questions. Simba, how do we know that light is red or blue shifted? How do we know that it wasn't its current color all along? How do we know it used to be a different color? So astronomers talk about this idea of redshift or blue shift. And essentially it falls into this idea of the Doppler shift. And I'm sure you know this experience, right? When an ambulance is driving towards you, you hear one sound, and then as the ambulance goes past you, then the tone changes, or like a horn, as they go past, right? And that is just the sound waves as they're moving towards you, they're bunching up and you're experiencing them at a higher frequency. And then as they're driving away from you, you're experiencing the sound waves less frequently and it sounds like a low frequency. And it's the same situation with light. And so if the object that is emanating the light is moving towards you, then the frequency of the light shifts towards the blue end of the spectrum. And if the object is moving away from you, then the frequency shifts towards the red end of the spectrum. And I guess the question is, if you see something that is blue, how do you know that it used to be red? How do we know that it's not just a blue star? So astronomers use this technique called spectroscopy. And what they do is essentially they look at the light from any object. You look at a fire, you can look at the sun, you can look at a light bulb, anything. And you then put it through a spectrum. And so the light gets expanded out and you get that rainbow. But the rainbow for different kinds of objects changes depending on the chemicals that are in it. And so you'll get these little lines inside of it, darkened areas where various wavelengths are able to be identified throughout that entire spectrum. And so chemists have gone and taken pretty much every element that they know of, burned it, shot it with a laser, done everything they can to get it to give off light. And what you get is this very specific chemical fingerprint. And so then astronomers will look at the light coming from some object, say a star that's moving towards us. They see the fingerprint, but they see that the fingerprint is shifted over slightly. And from that, they're then able to tell essentially how much that light has been shifted to the red or to the blue. And then they're able to use that to determine the velocity of the star or galaxy or whatever coming towards us or going away from us. Luis Velasquez, Fraser, future video idea. Can you do a comprehensive review of Starlink, especially with use from North America? I'm not sure I would ever want to do a comprehensive review of Starlink. So for those of you who don't know, I live now in the Canadian forest, fairly far away from the town that I used to live in, and there's no way to get a wired internet connection to where I am. It would cost like $1 million to convince the telcos to run the line all the way out to where we live. So I had to go with satellite internet, and the traditional satellite internet is terrible, but Starlink is pretty good. I'm sitting here recording this show right now in the back of a trailer, connected up with a router to my Starlink terminal, which is sitting outside, just sort of on a hill with a clear view of the sky. So what's it like living with Starlink? I would say it's effortless. Like almost all the time, it feels like we had a broadband internet connection. It's not quite as fast. And so if I'm like downloading like really big video files as we're like working with sending files back and forth with me and Chad, it's a little slower, but in many cases sort of it's fast enough. And then it's like the internet websites are the bottleneck and the bandwidth problems. I've been playing video games. I play like Path of Exile. And so the ping times are, when it's working perfectly, the ping times are about 35 milliseconds, which is fine, which is good enough for me to be able to play the game. I probably wouldn't be able to play a competitive game against other people, but I do get lag spikes and they kill me. And so my guy dies and I'm like, oh, lag. But most of the time, if we're just like watching TV shows or I'm doing research for Universe Today and uploading video and that kind of thing, you don't notice the lag. You don't notice the download, upload speeds. It's all pretty effortless. In terms of like maintenance, it's fairly power hungry. We needed to get power here before we could really run the dish. We were able to run it a little bit when we would like turn on our car and our car has an outlet in it. We could run the Starlink for a little while and download all the, download our TV shows and stuff and then turn it back off again. But now we've got power. And so we're able to just run it. Sometimes it will, if we get sleet, like snow, it seems to melt off of it pretty well. One time we had sleet come down and got like this much like ice rain on top of it, and it definitely knocked it out. And so I had to go out and clean it off. But apart from that, it's gone down twice in my time of using it now for more than a year. Went down for the longest was about an hour, and for like everyone on the entire earth. So, it's pretty expensive. I pay about $110 a month, which is about the same price that I was paying for my wired connection, but my wired connection was ridiculous. It was like gigabit internet, and now I've only got, say, 200 megabit internet. But I would say if you live outside of a city and you need internet and you can't get it from a wired connection, there's no better solution than Starlink. So that is my sort of user review of it. My astronomer opinion of it is less good, but we can save that for another day. Douglas Williamson. Why isn't the atmosphere of Venus a productive place for humans to visit and colonize? I mean, just trying to live in the air is really tricky. Like if you think it's hard to go to a place like Antarctica or Mars, where the conditions are really bad, all you've got to work with on Venus is the air. Because if you go down to the surface of Venus, obviously you will die. It's incredibly hot, incredible atmospheric density. It rains sulfuric acid. It's a very bad day. But if you go up into the higher atmospheric levels, you get to a point where the temperature and the pressure are kind of Earth-like. And in fact, the air that you would use to breathe would be a lifting gas. You could live in a balloon that is your air and float around in the cloud tops of Venus. But there's no other resources that you could grab. Like you wouldn't be able to get any metal or any rock or anything, really. Only what you could pull directly out of the atmosphere. But it's still a really massive gravity well. And so if you go down into the gravity well of Venus and maybe you're floating around and you want to fly out, well, you still need the same amount of rocket fuel to get out of the gravity well of Venus as you need to get out of the gravity well of Earth. And yet Earth has, metal to build rockets. And so it would be really hard to build anything on Venus in situ, like in place. You would need to bring everything. And so imagine what it would take to launch a rocket from Earth. It's carrying a rocket capable of launching from Venus, so you can even leave the atmosphere of Venus again once you're there. So there's just a million reasons why Venus is terrible, and we'll only be sending robots to Venus for a very, very long time. And I know there's like cool videos of like people flying around in blimps on Venus, but like maybe I can't even imagine a reason why you wouldn't just send a robot. There's like no reason to send a person to Venus at all. Like you can't even do geology. You can't even like go down and pick up a rock and lick it, which geologists like to do. Nothing. You're just sitting there staring out the cloud tops, flying your little dirigible. Doesn't make sense. So why isn't the atmosphere of Venus? Because it's terrible. It's terrible. There's nothing to do. J4H3AD. Simple question. What's your favorite thing about what you do? So I guess you're like saying like, what's my favorite thing about being a space and astronomy website publisher? Man, there's so many things that I enjoy about my job. Like, I don't know if people know my history too much, but before I started Universe Today, I was a tech entrepreneur. I worked at a couple of high-tech startups in Vancouver and went the whole venture capitalist route, leading fairly large teams, working with corporate clients, and hated it. Hated every part of it. I hated being beholden to investors. I hated having to work for clients, and I would have really good ideas and they would tell me that they didn't want to do them. And I didn't like managing a big team to the point that there was a lot of like politics and things like that brewing. And so as I was starting to work and build Universe Today, really on the side while I was doing my main job, my goal was to build an environment that matched my personality. So gave me freedom in terms of the time that I worked, the days that I worked, let me work on projects that I find really interesting. Let me use my capability directly, so if I think of a new thing that we want to add to Universe Today, it's a very quick meeting. I meet in my mind and we agree that it's a good idea and we go ahead. I wanted to make an environment for the team that works with me that was like really positive and really effortless for them and sort of a joy to work with me and the rest of the people on the team. And so I think that's it. I think for me, the thing I love the best is just having the freedom to run the kind of organization that I would want to work for. And, the fact that I happen to work on space and astronomy is fortunate. I love the field, but it's more about building an environment that I really enjoy. Chris Van Zegeren. Hey, Fraser, how do you determine when something is standing still in the universe, when it experiences the least amount of time dilation? That's a trick question, because the whole way that time dilation works is that everything is in relation to everything else. So if you and someone halfway across the solar system happen to be moving in such a way that the difference in your speed is very low, then you're going to experience very little time dilation. But the farther away you go between you and someone else, now you're moving apart at faster and faster rates. And so you're going to be experiencing different amounts of time dilation. And so there's no place in the universe that is not moving. Like if you take one side of the universe and another side of the universe, there's about a 60,000 year difference in experienced time just through time dilation. And you're just going to have various versions of that. So the place that is the least amount of time dilation is the person who's right beside you. Now, is there a place in the universe that isn't moving? And the answer is kind of no, but our local group is sort of moving compared to the cosmic microwave background radiation in a certain speed. And that's just through the motion of the galaxy compared to this sphere of cosmic microwave background that's constantly blasting at us. But it's not actually like the middle of the universe or a point of no motion or minimum motion. So you there's no place. Fernando Rodriguez, why do scientists at NASA website and other resources insist that the sun is an average star when 85% of the stars in the universe are red dwarfs, which are way smaller than the sun? I feel like it's a habit. Like the sun is just an average star and the solar system is just an average solar system. The Earth is just an average planet and you're not special. It's like the Copernican principle that we don't exist in any special part of the universe at any special time, that everywhere else in the universe is kind of roughly the same as where we are. The laws of physics are going to be the same. The amount of matter, the kinds of stars, the amount of planets, the size of galaxies, as far as you go in all directions, everything is roughly the same. But of course, Earth is very special to us, but in the grand scheme of things for the universe, we're not special. But there's nothing super extreme about the sun, so maybe that's where they're getting this from. But you're right, the vast majority of main sequence stars are red dwarfs. And main sequence yellow stars, G2 stars like the sun, are less common, and then really giant stars are even less common. So I don't know. I think it's just like they're just like saying like, not like it is exactly down. If you take all of the stars and the mass across the entire universe and you average them out and the sun is right in the middle. It's not like that. It's just like, there's nothing weird about the sun compared to any other star. Mike Jones, how do you know that we're not special? Have you been around the galaxy to see all the same Mars and Venuses everywhere to make that claim? So I guess this is a follow-on. This is the advantage of showing up to this live, is people can ask follow-on questions. This idea, the Copernican principle, that we are not special is just an assumption that just says the only way that we can make any kind of scientific progress about our understanding of the universe is to first assume that we're not special. That star in the sky that we can see is kind of like the sun. And it has the same process going. It has gravity pulling it in. It has light pressure pushing it out. It's made of chemicals left over from the Big Bang, as well as other subsequent star formation. It could have planets that are orbiting around it. And if you go far away, there's a galaxy, and that galaxy is filled with stars. And those stars are experiencing the same kind of gravity that we are here, and all of the electromagnetic forces. And you just have to make that assumption, because if you don't, then you can't understand anything, right? You're like, what's that galaxy made of? And it's made of purple. It's made of yes. And the power of gravity is dream. And you're just like, how do you make any progress? How do you make any kind of scientific understanding? So it's like scientists make that as this base assumption because any other possibility just leads to crazy town. And like, good luck making any kind of scientific progress. And yet here we are using the internet and mapping the cosmos and having GPS satellites and exploring the solar system using this basic assumption that the laws of physics are the laws of physics. And even if you go to Mars, the laws of physics are still going to hold. OMG poopy. What effect do the current sanctions on Russia have on space exploration in the future? This is still an unfolding story, and I'm going to give you some high-level ideas, but my good friend Dr. Pamela Gay and the team at Daily Space just did a really comprehensive episode about all of the implications for the war and what impact that's going to have on space exploration just in general. But I can give you just like a few examples. And it's not necessarily sanctions, although in some cases it's sanctions. The Atlas rocket uses Russian-built engines, and eventually they're going to run out. Now, Atlas has enough of those engines to be able to launch their remaining payloads. The Cygnus cargo vessel launches on a similar platform that uses Russian engines, and that's going to be a bit of a problem. They're going to need to come up with a new booster stage that's going to be able to launch the Cygnus up to the International Space Station. And the Cygnus is kind of special in the way that its thruster configuration is. It's very good at helping to give the International Space Station a boost. That said, SpaceX has said that they can fill in the gap with Cygnus, both in providing cargo, but also in helping to boost the space station. But we'll see about that. The head of the Russian Space Agency posted like a really weird video with really nationalistic music showing how the Russian segment of the space station could detach from the rest of the station and fly off for action and adventure. But it has very small solar panels, and how would it be resupplied? And there's all kinds of issues, but it could be possible that the International Space Station has to shorten its timeline significantly. The European Space Agency's ExoMars mission is a collaboration between the European Space Agency and the Russian Space Agency, and the rocket and the descent vehicle were all going to be done by the Russian Space Agency. So for the ExoMars mission, it's definitely going to be delayed. It's not going to launch in 2022. Maybe it'll launch in 2024 if things can be patched up. Otherwise, big chunks of that mission are going to have to be rebuilt. All of the Russian launch team members down at the European Space Agency's launch facility in South America have left. And so they're not there to support any Russian launches, which aren't going to be happening. We've seen OneWeb has had its rocket mission canceled, and now it's going to have to find a new launch provider to send up its satellites. There's a Russian mission that has a German instrument on board, and the Germans have decided to turn off the instrument. And so now they're no longer receiving science data from this instrument. So these are just like a few of the implications so far, but we're going to see a lot more implications if this drags out. You know, it's really heartbreaking for me, because if you've watched a bunch of these episodes, I've said this many times in the past, that I love the fact that the Russians and the Americans came together to build the International Space Station with support from the European Space Agency and the Japanese Space Agency and the Canadians, that it really is an international space station. And people from many different nations go up to the station and they hang out and they have a good time, that American astronauts learn Russian and they train at Star City in Moscow, and then they launch from the Baikonur Cosmodrome on a Soyuz rocket. Not anymore, though. Now they can launch from SpaceX. So it's the end of an era. And it feels like there were grievances simmering below the surface that have now come to light. And we're going to be experiencing the ramifications of this for a decade. More questions in a second, but first I'd like to thank our patrons: Andrew Block, Matt Masters, Paul Freeman, Lisa Bradley, and the rest of our 812 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. MNENG. I see that the US military will be patrolling cislunar space. That should be good for space technology development, but also will advance the militarization of space. Not good. Thoughts? So this is based on a story that came out in the last couple of days about the plans for US Space Force to send a patrol that's going to go around the moon. And I'm sure in your mind, you're imagining this space battleship that's going to be heading out from Earth and flying around the moon on patrol. But that's not what it's going to be. It's going to be like a satellite that has the capability to detect other satellites in the region and report information back to see if there's anything going on happening on the surface of the moon that maybe we're not aware of. But right now, like anything that's going to the moon has to launch from Earth, and the trajectories are very well known. So I wouldn't be super concerned. There's literally no military use of the moon. It's so far away. Like, yes, there is a military use of space, but it's really low Earth orbit and geostationary orbit. And once you get out to the moon, there's nothing out there to protect. There's nothing out there to patrol. And so it sounds more like them just developing an interesting mission that's going to allow them to test out further capabilities. And I wouldn't be too worried about it until there's like anything on the moon that is worth protecting, a base, a station, whatever, or multiple bases and stations. Like, go and see For All Mankind. And they've got this future where there's like a base on the moon for the US and a base on the moon for the Russians. And there are various tensions that go on. And then it would start to make sense to have some kind of military presence out at the moon. But for now, no. Liquid Flames. Any advice for an aspiring writer? Sure. You're not going to like it. Write a lot. That's my advice. It's like any advice for an aspiring plumber. Plumb a lot and you'll get better at it. Learning to write is a skill. It's a practice, and you have to do a lot of it. When I started my writing career more than 20 years ago, I was really good friends with a writer, a guy named Nigel Findlay, and he was a professional writer. And so he would write a lot of, like, if you play role-playing games, you play like Dungeons and Dragons or Shadowrun especially, and you just go look at the names on your books, many of them were written by Nigel Findlay. He was a very prolific game writer, and he would just write all day long. He would sit down, he would write for 8 hours. His goal was to write about 5,000 words every day. And so if you wanted an adventure, he would have it to you in less than a week. If you wanted a source book, you would get it in about 2 weeks. And if you wanted a novel, you would have it in about 6 weeks. And that he just wrote so fast and so consistently. And his advice was really learn to write fast, and then you'll learn to write well. And I've followed that advice. And so I'm a very fast writer. And that just comes from mountains and mountains of practice. Just being able to take the thoughts in your mind and turn them into words on the screen as effortlessly as possible. Writing is always going to be hard. It's always difficult. And, people experience this idea of writer's block, but like writing is a job, like any job. And the way you deal with writer's block is you sit down and you write, and it might be garbage, but you write. And then you're not into it, and then you get into it, and then you can't stop. And so that's sort of my advice to being a writer. How you get work in the industry, like if you've written a lot and you can show the work that you've written, you'll have a job anywhere. So my advice is start a blog, start something on Medium, or just start your own website, or start a WordPress website, or go and write really interesting posts on Quora or places where people are going to be able to see your work. And then you can just go to target some magazine or company or website like me and just say, here's my portfolio. Do you need a space writer, or do you need a whatever writer? And if your work is really good, then there's lots of jobs. I get people sending me their resume. I'm like, I don't care about your resume. Like, all I want to see is what have you written? And then I'll be able to get a sense immediately if you're a good writer and if you've got good ideas. And so write a lot. Challenge yourself to write more complicated things. And you can't go wrong. Shalaba Meta. Why a sudden probe rush to L2? Is it due to some new capabilities or new requirements or some other realization? So L2, I assume you're talking about the Sun-Earth L2 Lagrange point. And that, of course, is the place that is on the far side of the Earth. And so you've got the Sun, the Earth, and the L2 point. And it's located about 1.5 million kilometers away from the Earth. And that's the place where James Webb has gone. Like, it makes a ton of sense, right? Because James Webb has a sun shield. It needs to be maintained cold. And so at L2, it can put up its sun shield, and the Earth, the sun, and the moon will all be in the same location, blocked by the sun shield, and it'll be in eternal darkness. And there's been a bunch of other missions, and they all go to the same L2 point for roughly the same reason, which is that if you want to observe most of the sky, then you want to take the sun, the Earth, and the moon and hide them in one tiny little corner where they're always going to be there together. And then you get the rest of the sky. It is just a very useful place to go for astronomy, for space telescopes. But there's been a bunch of observatories that have gone to L2, not just James Webb. And anytime people are going to want to keep the sun, the Earth, and the moon clustered together in their field of view, you're going to see a spacecraft going to L2. Kobo Bunny. There might be a good chance for life around M dwarfs if they have large gas giants in the habitable zone with water-bearing Earth-sized moons. We don't know yet. Red dwarfs, M dwarfs, are dangerous little stars. When they first get going in life, they can release flares that are like 100,000 times more powerful than the kinds of flares that the sun throws out. And because these stars are smaller and give off less light, if you want to remain in the habitable zone around them, you have to be really close. You've got this double problem. You've got the stars giving off flares that are up to 100,000 times more deadly, and your planet is tucked in really close to the star, and it's going to take these flares right on the chin time after time. Does a gas giant protect you? And so like a gas giant might be able to generate a very powerful magnetosphere, but it's not going to be protecting the moons. Maybe you've got an Earth-sized moon orbiting around the gas giant. It's not like the magnetosphere is going to be protecting you. In fact, if anything, the magnetosphere of the gas giant, like Jupiter, is going to cause even more damage. Like, we know that the environment at Europa is quite dangerous because it's in very close to Jupiter, and it's got this very dangerous radiative zones that are going on. So I don't think that being a planet orbiting around a gas giant gives you any special benefit. Maybe if things line up perfectly and you happen to be behind the planet when one of those deadly flares gets blasted and you get protected, then every now and then you get saved, but there's no real special advantage. John Suffill. If our sun was formed in a huge nebula, and if there were several stars formed in the same region, where are those stars now? Astronomers assume that the sun formed in a solar nebula, kind of like the other stellar nebulas that we see out there, like the Orion Nebula or the Pleiades. And you've got this large cloud of hydrogen gas. It collapses down into multiple stars. Some of the stars explode as supernova, but you get lots of other stars that are smaller. And then over time, the powerful winds blow away all the remaining gas and dust in the region. And then you've just got these stars in this large amalgamation, a star cluster. And then over time, as the star cluster interacts with the other parts of the galaxy, the stars get stripped away. They drift away from this cluster over time until the cluster is completely broken up. And then the stars just turn into this long stream that wraps around the Milky Way. And then some of the stars go higher up the galactic disk, some go lower down, some move inward, some move outward. And so then they just really kind of mix up, and it's really, really hard to tell where those stars are. And astronomers have some candidate stars that they think might have formed in the same solar nebula as the sun. And so the clues they have, one is the velocity and direction of the sun. Like if you had a star that was moving in the complete opposite direction of the sun, that would be super weird. And you wouldn't think that they formed together, but a star that's in a roughly similar trajectory as the sun. And then the other thing is the chemical signatures. So all of the stars that formed in that stellar nebula formed out of the same raw material. And so you would assume that they would all have some version of the same chemistry and would have a very similar fingerprint. We mentioned this earlier in the episode, a chemical fingerprint. And so astronomers have found a couple that look like they have the same chemical fingerprint and also a very similar trajectory to the sun. And it's thought that maybe these stars were once part of the same solar nebula as the sun. Gaurav Sharma. Why is the Parker Solar Probe able to survive the sun, but the Venus landers have such short lives? The Parker Solar Probe is designed with a gigantic heat shield to protect it when it moves through the closest point of the sun. And it does it very, very quickly. It's kind of like a comet, and it flies in, does its imaging of the sun, moving at a really high velocity, and then flies back out to the top of its orbit, cools down, gets rid of all of that heat, and then comes back down in. And there's a couple of reasons. One is that you're out in space. And so the amount of energy that you're going to be receiving is different when you're out in space than when you're in an atmosphere and you're getting this conductive heat that is permeating your entire spacecraft. It has a very thick radiation shield that it hides behind. And this shield is getting blasted by radiation and heating up. And then it doesn't make it all the way through this heat shield by the point that the spacecraft gets out of the close danger zone. While, say, with the Venus spacecraft, they landed on, it's not like you can have a heat shield against this all-consuming, incredibly hot 450 degree Celsius atmosphere, intense pressure. So it's just really different environments. It may be very hot near the sun, but it's out in space. And so the only way for the heat to build up on your spacecraft is through radiation, and it keeps that shield in front of it. Hopefully we'll be able to see Venus spacecraft last a lot longer than the Veneris did, because I want to learn more about Venus. Flo K. If you had $1 billion at your disposal, what scientific project would you choose to realize? $1 billion isn't very much. Like to really do work. I think if I was going to choose a mission in terms of human space exploration, I would add rotating artificial gravity experiment to the International Space Station or the Deep Space Gateway, or launch something custom in a starship or something like that. Some way to start testing what long-term artificial gravity, with a rotating spaceship would do. Does it work? Or will you be sick all the time while you're in this process? Will it help deal with the loss of bone mass and muscle mass with this artificial gravity? What are the long-term implications of being in lunar gravity and in Mars gravity? Because we still don't know the answers to those questions. So I think from a space exploration point of view, that's what I would do. From a astronomy point of view, I would probably go with the sun shield. I'm getting pretty excited about the idea of launching a sun shield. Even a sun shield that can work with ground-based observatories would be pretty great. And it feels like a fairly inexpensive way to add a tremendous amount of capability. Now, I did an interview with John Mather like last week, and we talked about this idea. So I'll put a link to that episode and you can sort of see us working through that idea. But that's what I would probably do. And in terms of like scientific exploration, like planetary exploration, I really want to see a mission back out to the outer solar system. I want to see a mission to like Neptune or Uranus and to visit the moons. And so I would make that a pretty high priority. We've got some missions going to Venus, but in order to do that, they had to cancel the mission that could have gone to Neptune. And I'd like to see that mission back, because like if there wasn't already a helicopter going to Titan, then I would say Titan, but there is. And so I think what's left to be really explored is the moons of Neptune. David Waka, what's your most controversial opinion in astronomy or in a nerdy subject that you're into? I feel like I have a lot of controversial opinions. Like, I think we're alone in the universe, and I don't think that we're ever going to want to colonize any other planet in the solar system. So I feel like those are pretty controversial. Yeah, I'll go with those. Max, would tides be a problem around a habitable moon? It depends on the habitable moon. So I'm sort of imagining you've got, say, a sun-like star, there's a Jupiter-like planet in the habitable zone, and then you've got a Earth-sized world orbiting around that Jupiter as a moon, but it's habitable. So it all depends on whether the moon is tidally locked to the planet. If the moon is tidally locked, then it's always going to show the exact same face to the planet. And so it won't experience any tides. It'll be no tides. And it's possible that no tides is the problem. Many astrobiologists think the fact that Earth had tides early on was one of the reasons why life was able to develop from the ocean and shift over onto the land, because you have creatures living in these tidal areas. They get some air, some water, some air, some water, and they can move up the tide area to be able to live in air longer and longer and eventually be able to transition up onto land. So no tides might be a problem. But if the moon is orbiting around the planet and it is actually turning, then yeah, you'll definitely have tides. But it would become tidally locked almost immediately. So I don't think it would be a problem. Tom Gakwa, how would you go out to collect meteorites? A lot of the meteorites are found by amateurs here on Earth. And it's pretty tricky to find like a stony meteorite, because the stony meteorites look like a rock, and it's really hard to know the difference between a rock and a meteorite. And the best way to do that is to go to a place which is very bland, very similar, a place with lots of sand, like the Sahara Desert or the deserts of Australia, or a place that's covered in ice and snow, like Antarctica. And then people will travel around looking for anything that is strangely sitting out there that shouldn't be there. If you're driving in Antarctica and you're on this snowy plain and suddenly you see this rock sitting on the top of the snow, it's a meteorite. It has to be a meteorite. The metal meteorites are a little easier to find. One, because they're just so weird and heavy and feel like a piece of metal, but also you can use a metal detector. And so there are people who go into like large farmers' fields with a metal detector and attempt to detect any kind of metal under the surface. And they'll dig down, and what do you know? It's another old Roman coin or piece of garbage from a century ago. But sometimes there'll be meteorites found under the surface. So both are ways that you can go about it. Researchers have actually figured out ways to teach drones to find meteorites. The drones will fly around some landscape and then use their machine learning algorithms to look at various locations and find anything that looks out of the ordinary. And some of them will even retrieve them and grab the meteorite and bring it back to the researchers and drop it in their lap, and then they can decide if they think it is actually a meteorite. You can also find micrometeorites. So you can go and take the material that's falling on your roof, you can collect it up into a bag, like the debris that's coming on your roof. Now, most of it is going to be like pieces of coal or dust that's flown into the air, but you can look through it under a microscope and find particles that look very weird. And there's books that'll help you figure out which ones are meteorites. So it's a cool hobby. With the new studio that we're building, it's got a metal roof. And so my goal is to try and see if I can find some meteorite particles that are landing on my roof. But then I also need a microscope. But anyway, I'm definitely going to get into it. So I'll keep you posted. All right. Those were all the questions that we had this week. Thank you, everyone, for asking questions both in the YouTube comments throughout the week, but also showing up to the live show to ask your questions. We do the show every Monday at 5 p.m. Pacific time. So if you want to come ask your questions, come and join us. And the next episode should be somewhere around on my channel. I'll try to make sure that the event is set up. All right. We'll see you next week. If you want a single comprehensive resource for space news, you want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.